Okay, let's take a look at some counting techniques when we deal with outcomes that are equally likely. So when we have equally likely outcomes, we have a sample space with a finite number k of outcomes, and we say they're equally likely. So we calculate their probabilities by simply saying the probability of each outcome is 1 divided by the number of outcomes k. And so the probability of an event just depends on the number of outcomes that are contained within that event. So the probability of an event A is the sum of all of the individual probabilities of the outcomes in the event A, which is the sum of 1 over k, however many times A occurs, or A includes outcomes. And so that's S over k, where S is the number of outcomes included. So as an example, suppose a department has 11 professors, 4 of whom are women, and a professor is to be chosen at random to represent the department at a faculty senate hearing, with each professor equally likely to be chosen. College politics would suggest that it's pretty rare that each professor is actually equally likely to be chosen, but we'll make that assumption here. So what is the probability that a woman is chosen? Well, that event that a woman is chosen includes 4 outcomes, 4 out of 11, and so the probability that a woman is chosen is going to be 4 divided by 11. The multiplication principle states that if you have an ordered collection of n events, or an n tuple, if you will, where there are k1 possible values for the first element of the n tuple, k2 possible values for the second element, and so on, all the way up to kn possible values of the nth element, then the number of possible outcomes, or n tuples, is k1 times k2 all the way up through kn. As an example of this, suppose a family has just moved into a new neighborhood and they've chosen a medical clinic for their healthcare needs. Perhaps it's cheaper to have everybody within one clinic. So the family has to choose a general practitioner, a pediatrician, an obstetrician, and an allergist. There are 6 general practitioners, 3 pediatricians, 2 obstetricians, and 4 allergists. So how many different ways are there to choose a team of doctors at the clinic? Well, what we'll do is say n equals 4. We're choosing a 4 tuple of doctors, or a list of 4 doctors. We have 6 general practitioners available, 2 pediatricians, 3 obstetricians, and 4 allergists. And so we have 6 times 2 times 3 times 4, which equals 144 possible teams of doctors. So we can take that a step further. Suppose we wish to know the probability that Dr. Knapp will be chosen as the general practitioner, Dr. Jones will be chosen as the pediatrician, Dr. Sampson as the obstetrician, and Dr. Livia as the allergist. So that's 1 n tuple out of a collection of 144 n tuples. So the probability that that's the choice is 1 divided by 144, which is approximately 0.00694. Permutations are a specific illustration of the multiplication principle. So if you have a set of n objects, and we wish to determine a permutation, which is an n-element ordering of those n objects, how many different orders are there? Well, you can choose any one of the n objects for the first choice. Once you've chosen that object, then, you have n minus 1 choices for the second one, n minus 2 choices for the third one, and so on, all the way down to just 1 choice for the last slot. Everybody else has been chosen, or every other object has been chosen. So you have n times n minus 1 times n minus 2, all the way down to 1 possible orderings, and we denote that number by n factorial. As an example of a permutation, suppose a professor is supervising 6 teaching assistants. He's just given an examination and it had 6 questions, and he wishes to have 1 teaching assistant grade each of the 6 questions. So he doesn't want to have a teaching assistant grade 2, he doesn't want to have any teaching assistants grade none. He's going to assign 1 teaching assistant to each question. How many different assignments are possible if each assignment is equally likely? Well, he's going to have 6 choices for the first question, 5 choices for the second, all the way down to just 1 choice for the last one, since everybody else will have been assigned, and 6 factorial equals 720. So there are 720 different ways of assigning TAs to the question. Sometimes, however, that's not how it works. Maybe the professor actually has 12 teaching assistants and he only has 6 questions. So if he's going to assign 1 question to a teaching assistant and no teaching assistant to more than 1 question, then he would have 12 choices for the first question, 11 for the second, and so on. And so this gives him an astounding 665,280 possible 6 TA assignments here. Notice that we still consider this a permutation, but we're doing a permutation of 12 objects where we select only the first 6. So in the general case, if we're choosing k ordered objects from a set of n objects with no replacement of objects after selection, the number of ways to select that is n times n minus 1, and so on, all the way down to n minus k plus 1. Or, more concisely, n factorial divided by n minus k factorial. So I mentioned sampling without replacement, right? We didn't assign the same TA to 2 questions. So when we're sampling without replacement, we will use permutations. If we're sampling with replacement, then the same TA could be chosen for multiple questions, for instance. Then we would have a case where, for instance, you could have any one of the 6 TAs assigned to the first question, any one of the 6 TAs assigned to the second question, and so on. So you've got 6 choices in each slot, or 46,656 choices. So only 720 of those 46,000 choices has 1 TA for each question. With 12 TAs available, you'd have over 2 million, almost 3 million ways of assigning the 6 question.